Okay, so today we are going in the direction of trying to understand the structure of the formulas for the mixed moments and free variables better. And up to now, we understand the special case when the kernel of the indices of our variables, when they are non-crossing. Then we can just factorize the whole moment according to the block structure by just factorizing one block after the other. Beginning with a block which is a kind of interval. We take it out, and we find another interval, take it out, and so on. Good. But for understanding the general structure, I mean, this is much more complicated, and at the moment it's not clear how to describe this. And in order to see maybe more structure behind this, I want to look now on the free central limit theorem. And in particular, compare this to the classical central limit theorem, because this also shows us somehow the difference between classical and free, particularly in combinatorial terms. So last time I recalled the classical central limit theorem. Just write this down again. And we formulate this in our non-commutative language. I wrote this down last time, so let me just recall. So a phi is a non-commutative probability space. Then we have variables there, infinite sequence, ai, which is indexed by natural numbers. I think last time I wrote I here, but of course it should be an infinite index set, so let's say n. So I have an infinite sequence of natural numbers, and I assume they are classically independent. So last time I wrote precisely what this means, but it should be clear. So this means the variables commute here in classical context, and they are independent means they factorize. So if I have a phi applied to a product, let's say a product of powers of them, then it factorizes according to them. And in classical context, of course, I can write, because of the commutativity, I can bring any such mixed moments in the form that I have a power of the first variable times the power of the second variable times the power of the third, and so on. For a finite number, and this just factorizes. Good. Okay, so that's classical dependence. And then we have to make some assumptions on the distribution. So first of all, we assume that they are all identically distributed. All AI identically distributed. This is an assumption which can be weakened, but it's for the proof we are going to do, it's very good to have this assumption, and it's maybe the most common form of the central limit theorem. And then, so this means every AI has the same distribution, and about this distribution we make two assumptions. We make an assumption about the mean and the variance. It's very important about the mean. So we assume the guys are centered, so phi of each of them is 0. And then for the variance, this is more or less a normalization. So it must be a finite number, and we normalize this to 1. Of course, the second moment and the variance of the variable is the same because the mean is 0. Good, so that's the frame, the assumption. And then what is one interested in is classical context, or in the central limit theorem context, one is looking on the sum of the variables, and then one normalizes it by the square root of n. And the question is, does it converge to something? And of course it does. So we take Sn, this is the sum of the first n variables, and we normalize this by the square root of n, and then the statement is that this guy converges to a normal variable. Okay, and the notion of convergence in our algebraic setting, the only meaningful thing is that with this we mean that we have the convergence of all moments. So what we are claiming is that the limit of a moment of Sn, let's say the kth moment, that this converges to something which you can describe very precisely, and we say this variable converges to a normal variable, and this means it converges to the corresponding moment of the normal distribution. This we can write down very explicitly. So this is normalization, and then it's an integral over of r indicated moment, and the density of the normal distribution is e to the minus t squared over 2 dt. But it's a normal distribution of variance 1. Of course, I mean, knows I mean this is somehow the density of the normal distribution. And we can also write down explicit formulas. We can calculate this integral. Maybe you should do it at least once in your life. So namely, this is explicitly, of course, this is an even distribution. So this means the odd moments are 0. So this is 0 if k is odd. And if k is even, then it's a nice product formula. It's k minus 1, it's k minus 3, and so on, up to 3 minus 1. Okay. Even. So it's a kind of factorial, starting at k minus 1, but going down in steps of 2. Okay. And so this is a nice formula which you can just calculate this. And maybe one thing which might be surprising is those are really natural numbers. Which might give a hint that there is some combinatorics in the background. Because usually if you see natural numbers, where a priori maybe there's no reason why they should be natural numbers, maybe they are counting some objects. And we will see if this is the case. Good. But anyhow, so that's the classical central limit theorem. And now we want to do a free version of this. And this was what Roland did in the very beginning. It was one of the first real results in free probability theorem. So let me first formulate this. So this is the free central limit theorem. This is due to Roland. And it's from 1985. So this was at the very beginning. Good, so what is the statement? Of course, I mean, it is clear what we should do, at least in the assumptions, we should replace independent by free. And we have already written the classical version in an algebraic way, so we just essentially replace exactly independent by free. So assume we have a non-commutative probability space, and we have a sequence of random variables. Random variables are just elements in our algebra A. So let I the random variables in A, indexed by natural numbers. So we have an infinite number of them, and we assume they are freely independent. Let those guys be freely independent. And again, we make the same assumptions on their distribution of the individual variables. I mean, of course, freely independent means I can calculate all these moments if I know the distribution of individual variables. So I mean, I must assume something on them. And of course, again, make the same assumptions. So we assume they are identically distributed. That first of all AI are identically distributed. Which means all their moments are the same. And now we make again some assumption about the first and the second moment, as before, as in classical context. So namely, the first moment is 0, and the second moment is normalized to 1. They are identically distributed, so those moments are the same for all our variables, for all I in A. Good, so that's the same assumptions as in the classical context, only independence is replaced by freeness. And again, we are looking on the same quantity. We take the normalized sum of the first n variables, as before. This n is the sum of the first n of my variables, and I normalize it by the square root of n. And again, I ask, does this converge to something? And And again, convergence means, in our context, convergence of moments. So, I mean, first I make the statement, yes, it converges to something, but of course I also want to describe this something. And these are, again, moments of a very nice distribution, a very nice probability distribution. So, this is the statement. So, Sn converges, again, distribution, and converges to what we call a semicircular variable. It converges to semicircular variable. What does this mean? This means it converges to distribution which looks like a semicircle, or maybe some ellipse, but you can write it down explicitly, like in the classical case. So the limit, if n goes to infinity, phi Sn to the power k. We're looking on the moments of Sn, so let's say the kth moment, and this in the limit converges to the corresponding kth moment of a probability distribution, but this time this probability distribution is not living on all of R, but it actually lives on a compact interval, namely with our normalization from -2 to +2. So we have the kth moment of this. And the density of this guy is 4 minus t squared. The square root of this t. Okay, and I mean this density looks like a semicircle. That's why we call it a semicircle. And again, we can calculate those moments very explicitly. So again, I can just do the calculation. And in this case, I mean, you will be asked in the assignment to do the calculation, because that's really something which you should not only do in theory, but also in practice, at least once in your life. Okay, so again, I mean, this density, yeah, so maybe, so how does it look like? I mean, so this is a density, which looks like a semicircle, so it goes from -2 to +2. And again, of course, it is even distribution, so the odd moments are 0. And, okay, for the even moments, we again get some natural numbers, namely, by the way, like this, 1 over m plus 1, and then 2m choosing binomial coefficient, and k is equal to 2. K is e. Okay, so these are natural numbers for each year. Actually, very famous natural numbers, namely the Catalan numbers, and we will define them later again. Good. Okay, so that's the statement. And you see, it's very, very parallel, but maybe in this formulation, it's a bit unclear. I mean, okay, so it's clear that that this semicircle is the free analog of the Gauss distribution, by this theorem. I mean, the normal distribution is, why is it so important and why is it a normal distribution? Because it appears in the limit of the central limit theorem. So what shows up in the limit of our free central limit theorem is the analog, which would also be equally important free probability theory. So it's the analog of the classical distribution. But analytically, I mean, we get here the semicircle, and here we have this. And I mean, from this point of view, it might not be so clear if you don't know that it's the limit of the central limit theorem, why these are the same. But so we are going to prove now this by combinatorial methods. Then actually we will see much more clearly why this is the analog of this. In the combinatorial terms, it's much clearer why this should correspond to this. And we will also understand why the moments of them are really given by natural numbers. Okay, so let us do the proof of this. And let us do the proof essentially of both theorems at the same time. We really want to see that we are really doing very parallel things to classical probability theory. So this means at least in many situations the proof are somehow parallel. At least in a combinatorial point of view, many things go. Okay, so we do the proof. Actually both the classical and the free central. Good, so this means at the moment we assume that we have a situation, we have our AIs which are either classically or freely independent. And I mean for the argument at the beginning, it means it works for both. And only at the end we have to specify in which situation we are. I mean there must, of course, there must be some difference at some point, no? But this will only come at the end. So we assume that our sequence of random variables are either classically independent or freely independent. Good. So what do we have? What do we want? I mean, what we want is we have to calculate the moment of our variable Sn in the limit. So what we should understand is the kth power of Sn and phi applied to this. And see whether we can understand the limit. So let me look on the nth power of k, of Sn, and apply a mistake to it. And this normalization square root of n, maybe we leave it out for the moment and only take care of it later. So let me just first look on phi of the k power, not of Sn, because Sn contains normalization. So let me just take a1 plus an to the power k. That's the quantity which we have to understand. At least in the limit if n goes to infinity. Yeah, what is this? So I have here a k-fold product of the sum of a1 up to an, and of course I multiply this out and I will get all possible products of the a's. So I get k factors multiplied with any distribution of the indices here. So what this is really a big sum, and so I get all possible multi-indices here. Which is multi-index, or I as a function from the set 1 to k to the set 1 to n. This is nothing else than a multi-index. And here I get phi of a, of 1, a2, up to a of ik. So this I is my multi-index. So this is a number between 1 and k, this is a number between 1 and k, and so on. I manage this out and I have to sum over all possibilities of the distribution of the i's here. Good. And of course the problem is, if n goes to infinity, this sum is getting bigger and bigger. No? I'm getting more and more terms, and I mean, it's hard to control this. And the crucial insight is now that actually many of the terms, the numbers which I get here, are the same for different i's. No? So if all the multi-indices would give different contributions, I might be able to control, for every multi-index I might be able to control the limit if n goes to infinity, but if each of them gives a different contribution, it would be very hard to see what they give all together. But the crucial point is that actually many of them give the same. And why do they give the same? Well, when do they give the same? They give the same if their kernel is the same. So we have seen that in our factorization, the crucial information which we need about such a mixed moment is the kernel of the multi-index. So this means, at least we can hope, that actually it's a good idea to collect all those multi-indices into classes which correspond to partitions. So this means I'm taking the partitions of k, and then I'm summing over all I, which have this pi as their kernel. The kernel of such a multi-index, that's a partition which tells me whether indices are the same and whether they are different. So this is a partition of k. So this means I'm summing over all partitions of k, and then I'm summing over all multi-indices whose kernel is exactly this given partition pi. And then still, because I have here my some phi of A1 up to phi of k, but now I'm claiming that if I'm fixing the kernel of I, then this value here is always the same. So actually, this value only depends on the kernel. So this only depends on phi, not on the actual value of the mighty index. Okay, I'm claiming that this actually is only depending on pi. So it's a function of pi. That we write g of phi. And in order to be able to make this, the crucial observation is that this depends only on pi. So this means if I have two multiplices which have the same kernel, then their corresponding phi is the same. So this means that phi of I1 up to Ai k is the same as phi of Aj1 up to Ajk. If the i's are the same positions where the j's are the same, then this decrease. And why is this the case? This is the case because we know that free independence and also classical independence are rules for calculating mixed moments out of the distribution of the individual moments. But the individual moments of all my variables are the same because we have an identical distribution. So this is both our assumptions, either classical or free independence, are rules for calculating joint moments of my variables from the individual moments. Individual moments are all the same because we have identically distributed. Okay, so maybe just an example to really make this clear. What I'm saying here. So, for example, let's look on the joint moment of the form A1, A2, A1, A1, A2, A3. So this is 1, 2, 3, 4, 5, 6. So this is for k equal to 6, multi-index. And what is the kernel of this? The kernel is the partition which tells me where the indices are the same. So here's one block, because at those positions I have the same index 1. Then here I have index 2 and 2. And here I have the index 3. So the kernel of this multi-index 1, 2, 1, 1, 2, 3 is this guy. And I'm claiming whenever I have a joint moment which has the same kernel, then I get the same contribution. So for example, another situation like this would be A7, A5, A7, A7, A5, A2. So here I have the index 7 at those positions, I have the index 5 at those positions, and I have the index 2 here. So it has the same kernel. So I mean, at this position I have the same index, and whether it's index 1 or index 7, this doesn't matter. And why doesn't it matter? Because free, I know the variables are free, which means such a joint moment is given by a formula in terms of the individual moments. Okay. And of course on this side, this joint moment is given by the same formula in the mixed moments, in the individual moments. But here this formula, I mean, in this formula I have to plug in the individual moment of A1. On this side I have to plug in the individual moment of A7. But those moments are the same because A1 and A7 are identically distributed. Then A2 has the same distribution as A5, and A3 has the same distribution as A2. So this formula gives me really just the same result. And of course, in the classical case, it's the same. I also have a formula. In the classical case, I mean, this would be very easy because this is then the third moment of A1 times the second moment of A2 times the first moment of A3. And here it's the third moment of A7 times the second moment of A5 times the first moment of A2. And again, the third moment of A1 is the same as the third moment of A7 and so on. Good. Okay, so again, this is true in general. So whenever the kernel of such a multi-index is the same, then I get a number. And you see, I mean, I know there's a formula, even if I don't really understand precisely how the formula looks like. For this argument, it's enough to know that there is a formula in the individual moments. So I mean, in free case, I don't really know the precise nature of this formula, how to express this in moments of A1, A2, and A3. But I know there is a precise formula. It's the same on this side and on this side. Good. Okay, but then we can continue with our calculation. So let me see. So what do we have? We continue here with this calculation. So I'm writing the sum over pi pk in partitions of k. In k are the positions. I'm looking on a product of k elements, and k is the positions 1, 2, 3 up to k. And the partitions tell me whether indices are the same and whether they are different. Then for each pi, I get, so for all multi-indices corresponding to pi, I get the same contribution, g of pi. Then of course I get this distribution for each multi-index which has pi as its kernel. So I have to multiply now this number g of pi with the number of possibilities of multi-indices. Picture it up here. So this is times number of multi-indices I, functions from k to n, for which the kernel of I is the given pi. Okay. And now you see that actually now the dependency on n, I mean, once again, n should go to infinity, so we have to understand what happens in this equation. The only dependency of n is here. This here is a summation over partitions of k. K is fixed. That's the moment which we want to consider. It's only here that we have to see how many multi-indices do I have which have a given kernel. But this is actually very easy to count. So how many possibilities are there for multi-indices of having such a kernel? I mean, the indices which I have at my disposal are 1 up to n, and so I mean, having this as a kernel tells me, I mean, at this position I must have the same index. Okay, so and I mean, let's start here. So let's take this block, and I have n possibilities for putting an index here. Then for the next block, I mean, I know this and this position, it must be the same index, and of course it must be different index from here. So I have n minus 1 possibilities for putting index here. And then for this block, I mean, I have more possibilities, but the two indices which I have already used, so I have n minus 2. So for each block, I have so many possibilities. So this is very easy. You see what this is. So for the first block, I have n possibilities. For the next block, I have n minus 1 possibilities. Then I have n minus 2 possibilities, and I'm going down until I have given the number to the last block, which is then n minus the number of pi minus 1 possibilities. And these are just the number of blocks many factors. And if n is large, then subtracting n or 2 doesn't make a big difference. So for n going to infinity, this behaves like n to the number of blocks. I mean, if n is large, then I can more or less ignore, and I shouldn't put the same number of different blocks if I just count the numbers.
Maybe there should be plus, no?
Maybe there should be plus. If the number of blocks is 1, yeah. Okay, plus. Good. Yeah, and so this means, that that what I have here is actually a finite sum, which doesn't depend on n, some coefficient, and then I have here something which grows in n, actually n to some power. And now you see why we should also divide by some power of n, namely in order to balance this here. Of course, I mean, this here would go to infinity if I would have a balancing effect. And of course, I mean, we have here sums of different powers of n, and the limit, it is clear that the leading order will survive. And our normalization should normalize the leading order to 1, to something finite. Good. Okay, but so I mean, a priori, so you see, we divide by square root of n in the central limit theorem. A priori, it looks as if this would be a bad choice, because in the worst, what is the worst case which we can get? The worst case is if pi has as many blocks as possible, and this could be k. If we just have singletons, then the number of blocks is k, and then we get here n to the k. But then I'm dividing here by Sn, I'm dividing by the square root of n to the power k. I'm dividing by n to the power k over 2. Not by n to the k, but by n to the k over 2. This means I'm not cancelling those terms, and so the only chance we have is that actually those terms don't really contribute, because we also have this factor. This factor might be 0. And that's what we have to see, and actually this guy is 0. If this is not 0, I mean, then you are in the context of the law of large numbers. And there actually, in the law of large numbers, you're dividing by n. Okay, but for the central limit theorem, we have more information. In particular, the first moment is 0, and this will guarantee that this factor, in the end, will show us that only power n to the k over 2 will contribute. Good. But so, that's crucial observation now. The point is, yeah, so you see that singletons, if we would have singletons in our partition, then we can have a high number of blocks. If we want many blocks, blocks should be as small as possible, and I mean, the smallest possible blocks are the singletons. Singletons are blocks which only consist of one number. And so we should see that singletons, that partitions with singletons don't contribute. So let us consider pi which has a singleton, so that we can get rid of this. Yeah, so we consider now a situation where pi has a singleton. And the singleton, I mean a block of size 1. This means I have a block pi which has size 1. Also the number of elements in V is 1. Let's say give me number to this element. So let's say V consists only of S. I mean, V is a partition of 1 up to K of the positions. So S is a number between 1 and K. Okay, so we assume this for some S. Okay, then we have for the G of pi. Our goal, of course, is to see that this G of pi beta should be 0, because otherwise we will have problems. But this G of pi, so what is this? This was the common value of all joint moments where the kernel of the multi-index is this pi. So I should take the multi-index with kernel pi. So let's say I take the multi-index I, such that the kernel of this guy is this pi, which I'm considering. So then this G of pi is the same as phi of the product of my A's indexed by this multi-index. So I of 1. And of course this position S is special, so let me write it out here. I of S minus 1. And then I have the position I of S. Then I have the position S plus 1 up to I of K. So I'm multiplying k of my variables, and they have indices here. Good. And so what is now the condition that this kernel has a singleton at this position? This tells me that this I of s, that's the index which appears here, doesn't show up among the others, because it's a singleton. So I have a block here which only consists of this guy. It's not connected to anything else. So this means this I of s is different from all the other indices appearing here. And then you see that I'm more or less back in my usual factorization situation, where I have something element here which is free from all the other guys which I have around. Because all my variables are free, so if this variable only appears here and not among the others, then it's free from the other guys. So this element here is free from the rest, from the other elements, because it only appears once. Appear once. Okay, and then we know, so now I have the situation, I can give a new name to this product, a new name to this product. I can call this A1 twiddle, A2 twiddle, and I can call this B, and then I have exactly the situation that this B is free from the A1 twiddle and the A2 twiddle. And then we have this factorization rule that such a phi factorizes into phi of this times phi of this times this. So this is one of the simple factorization rules which we understand for free variables. Which actually is 6. So this factorizes into phi of AI1 up to AI s minus 1. And this is gone, and I'm continuing with AIS plus 1 AI k. And then times phi and this is the rule of freeness, and of course, we might also be in a classical situation where things are independent, and then we have, of course, the same. Because for independence, we have the same factorization. This is a rule here for this situation, which the rule is the same for classical and for free independent variables. So this is by 1/6, or in the independent case, and the same rule for classical case. Good, but now you see that this is really 0, because we have here phi of our variable. So we have the first moment of one of the variables, and the first moment is 0. So you see, it's very crucial in the central limit theorem that we assume that the first moment is 0. So this guy here is 0, which means that the whole thing is equal to 0. So you see that g of p really is equal to 0 if we have a singleton. Singletons would be the case which gives us many blocks, but we cannot have too many because we are excluding singletons. So the conclusion of this is first, if we have a singleton in our partition, so this means a block which only contains one element, and this implies that g of pi is equal to 0. Or the other way around, if we want the situation that g of pi is not equal to 0, and that's the one which will contribute in the end to our sum, then it cannot be that there are singletons. So this means the block cannot have any singleton. This means that any block must at least contain two elements. Okay, it contains one, it's a singleton, so that's not what we want. So singletons means every block contains at least two elements, but this means the number of blocks cannot be too large, because if I want a partition of k elements, and each block contains at least two two elements, I can have at most k over 2 blocks. Good. So we see if we are only interested in pi's for which g of pi is different from 0, then we need that for all blocks in our partition, this block must have at least 2 elements. Yeah, but this means, on the other hand, that the number of blocks for such a partition can be at most k over 2. So for such a partition of k numbers, we have the number of blocks is less than k over 2. Good. And k over 2 sounds good, because I mean k over 2, n to the k over 2 is exactly what we are dividing by, this our normalization square root of n. So, yeah, so what do we get now? Yeah. So we're looking, and now we're looking on Sn. Now I put in the normalization, because now we really want to go over to the limit. So let me now look on Sn in k. There I have, in addition to my formulas before, I have this n to the k over 2 coming from my normalization in Sn. So I have an extra factor n to the k over 2, which comes from my normalization. And then I just have what I calculated before, which was the sum over all partitions of k elements. But now we know that we only have to sum over partitions which have at most k over 2 blocks. Because if this is not the case, this g of pi, which we have here, is equal to 0. So we can throw away those guys. Okay, so we only look on those where we have at most k over 2 blocks. And then I have here the number of multi-indices from k which have this pi as their kernel. So the kernel of I is equal to pi. But we saw before how this behaves in n. So then in principle, we have for each block, we have n possible choices. Of course, we should avoid that different blocks have the same, but for large n, this doesn't play a role. So for large n, this behaves like n to the number of blocks in good. And so now we send n to infinity. So what do we get? So, okay, I bring those two n dependencies together. I mean, this sum here doesn't depend on n. So this is always the same sum over pi partitions of k. I can assume that the number of blocks is less than k over 2. Then I have g of pi. And then I have here the limit n going to infinity of this guy here, n to the number of blocks of pi divided by n to the k over 2. Okay, and this limit, of course, we know what this is. I mean, different powers of n. What survives, this is the leading order. Okay, and we already know that this order here can be at most k over 2. This doesn't explode, but in this limit, it's exactly the order k over 2 which survives, because then this limit goes to 1. If this here is less than k over 2, this limit goes to 0. So this limit here, this is 1. If the number of blocks is exactly k over 2, and otherwise, if the number of blocks is strictly smaller, it is 0. Good, so we are surviving the sum of k over pi, and you see in the limit, we just get here 0 or 1 from these combinatorial guys. And we are just surviving with the guys where the number of blocks is equal to k over 2. Okay, but actually, we also here, we're looking on partitions which have no singletons. The singletons are also excluded. So this means we have here a situation, what survives in the limit, we have that the number of blocks is exactly equal to k over 2, and we don't have singletons. Yeah. But this means that each block must contain exactly 2 elements. So what we have here is what we could call a pair partition or maybe a pairing. So we have seen, in the limit we only have contributions from guys which have no singletons, and on the other hand, they must have exactly k over 2 blocks. But if I want a partition of k numbers into blocks, and I don't allow singletons, and I want exactly k over 2 blocks, then this means every block must contain exactly 2 elements. And that's our final general result, let's say, about this calculation. Thus, we have, and again, maybe the argument is that what survives. So what do we have? We have partitions which survive. Those partitions must have exactly k over 2 blocks, but on the other hand, they don't consider singletons, and this means that pi is a pairing, which I will define now, but which says of course that each block contains 2 elements. So what we get is that the limit of phi of Sn to the power k, n goes to infinity, is given by summing over pairings, and I denote them by putting the 2 as a sub-index to p of k. So this is p sub 2 of k, and then I get a contribution g of p. And this p sub 2 of k, these are the pairings. P sub 2 of k denotes what usually I'm going to call either a pair partition partition where each block contains 2 elements, then essentially I'm pairing 2 elements each block. Also P2K by definition, 2 partitions of K where the size of each block is 2. So this gives us already quite a bit information in general. We have quite a nice combinatorial formula, and you see essentially we are summing over pi, but of course we still have this g of pi. That's something which we should see what this is. But before we go to this, maybe the first thing we see is of course that if k is odd, then there are no pairings. I mean, for odd number of elements, I don't have pairings. I cannot distribute an odd number into a number of pairs, which means there's nothing to sum over, so this here is just 0. And so you see that we get already, without even going further into this, that both in the classical and in the free case, we have to have an even distribution. So P2 of k is the pairing, so this is the empty set, so there is no such pairing for the case when k is odd. This means that this formula tells us that the odd moments are also yes, the limit when we go to infinity I of Sn to the power k is equal to 0 for k odd. Actually, this is in both cases. I mean, still, we're looking for the classical and the free case at the same time. And up to now, we have not made any differentiation. All the arguments were the same. But of course, now we really want to look what are the even moments. And we know they are different. Now we have to distinguish between whether we are in a classical case or in a free case. And of course, what the difference will be that this g of pi will be different in both cases. So we have now to look at those. And let us first look at the classical case, because there things are very simple. So now we assume that our variables are all classically independent, and we have to see what is g of pi for each pairing of k elements. So we look at the classical case, and there now what is g of pi? G of pi is phi applied to a product of the variables where the kernel of the indices, the multi-index, is given by the pi. So this means what we are looking at now are product of elements where each variable appears exactly twice. Because I mean, the kernel tells me the positions where the same variables appear, and if each block has two elements, this means every random variable appears exactly twice. So what I have to do to calculate g of pi, I take just the situation I have a pairing, and then I just have to look at the situation where exactly each variable appears twice at this position of the pairing. But if I'm in a classical case, I have a product of elements appearing twice. Where they appear doesn't play a role because I can commute everything, and then you see that I just have a product of the squares of my variables, and they are independent, so phi factorizes. So I just get the product of the second moments of my guys. The second moments are normalized to 1, so what I get is just that this is equal to 1. And this is independent of pi. Of course, this is true for everything. So in the classical case, we just have that this g of pi is the same for all pi, and it's actually 1. So here we get the normalization of our second moment. Because in general, we would have to multiply the second moments of our variables. So we have g of pi is equal to 1 for all pairings which I consider. And so what we get in this case, we have, and of course let's say k is given, because otherwise it's 0. We know that the limit n going to infinity of k moment of Sn is given here by what? So we have to sum over all pairings, and then each pairing gives us a contribution g of pi, but for each pairing this is 1. So we are just summing over 1 for each of the pi's here. But this means we are just counting how many elements we have here. So this limit here is nothing else than the number of elements of P2 of k. And of course these are natural numbers, and now you see that our claim that we get here the moments of the normal distribution, we still should see that those numbers here are actually the moments of the normal distribution. But the number of pairings is again very easy to count, because if I have a pairing, I want to count how many pairings do I have of, let's say, k elements. Also, how many? So I have numbers 1 up to k, to know how many pairings do I have and how can I produce a pairing. I mean, this means the first element, let's say, must be paired with something. But with something, I have k minus 1 possibilities. If I have, after having chosen this first pair here, then I'm left with pairing the remaining guys. Okay, then, I mean, for the next free guy here, I have now k minus 3 possibilities. Because I have here left k minus 2 ones and this one, so I have k minus 3 possibilities. After having chosen this guy, I look for the next free one, and for this I have k minus 5, and so on. So I'm multiplying this going down in steps of 2, because I'm always removing 2 points, which I have paired, going down to the last one. And this is exactly the moments which I told you are the moments of the normal distribution. But here you see that those moments are natural numbers. There's a reason behind this, and the reason is that those moments are actually counting the number of pairings of k elements. Yeah, okay, but this is a proof of the classical central limit theorem. So this proves the classical central limit theorem, which was 2-7. Good. Now, of course, our main interest is in free case, and there the period, of course, be different. Not all g of pi will be equal to 1, because otherwise you get a normal distribution. So we have to try to understand what is going on here. In free case, so I'm assuming that my variables are free, and there it turns out that again, there are simple values of g of pi, and actually there are only 2 possibilities. G of pi is either 0 or 1, and when is it 1? It means 1 in the non-crossing case, and it's 0 otherwise. So in this case, we have for, let's say, case even number, even, and pi pairing this even number to m, that actually is g of pi takes on only 2 values, namely 1 and 0, and this distinguishes exactly between the non-crossing and crossing partitions. So it is 1 pi non-crossing, and it is 0 if pi is crossing. So why this? I mean, first of all, if pi is non-crossing, then actually we know that it is 1, because in this situation we know that we have the same factorization as stochastic variables. So again, I have a product of variables, each variable appears twice, and if my pi is non-crossing, this means I must find intervals, which means I find the 2 variables sitting beside each other. Okay, then I factorize this out, this gives me 1. Then if it is non-crossing, I must be able to find another pair which is sitting beside each other, and so on. I do this interval stripping until nothing is left. Okay, so this is clear that if pi is non-crossing, I will get the 1. And y is 0 for the other ones. That's maybe also it's more or less a definition of freeness. Let's see. So first for non-crossing pi, this follows from 3.6.1. This was the situation that if my kernel of my multi-index is not crossing, then I have this factorization, which is S in the classical case. Okay, so for crossing pi, so how is it for crossing pi? There it might be that I also find some pairs which are neighbors, and then I can also factorize. So I can do this interval stripping up to some point. I might be able to find at least some neighbors. So for crossing pi, do this interval stripping, which means taking out intervals. In this case, intervals are just pairs, because the blocks have size 2. So we do this interval stripping until we arrive at a situation where we cannot continue further. And this means that no two neighbors are the same, because otherwise we could strip further. So we do this interval stripping until we arrive in a situation where neighbors are from different algebras, or neighbors are different variables. And neighbors, let's say, are from different algebras, or maybe neighbors are different random variables. But then I have a situation where I have a product of my random variables, and neighbors are different random variables. But on the other hand, they are all centered, so phi of each of them is equal to 0. So I'm exactly in the situation of the definition of freeness, and freeness tells us that phi of such an alternating product of centered guys is equal to 0. Also, this means that phi of such a situation is equal to 0. There's different algebras. Continue here. Phi on this is 0 by definition of freeness. Okay, maybe let me make an example of this just to see this. Yeah, so you see that in the classical case we have a factorization of all situations. There it doesn't really matter what pi is because everything commutes. In the free situation, I mean, we have situations where you can do more or less the same as in the classical situations, it's the non-crossing ones. And in the other situations, it's actually our definition of freeness, which more or less tells us that those guys are equal to 0. Yeah. So maybe here's an example. Such a crossing situation. Also, for example, let's say we look on A1, A2, A3, A3, A1, A4, A4, A2. So I mean every variable should appear twice. So the 3 is here and here, the 4 is here and here, the 1 is here and here, and the 2 is here and here. So this is a crossing pairing. And of course, I mean, there are some blocks which are neighbors. So they can be removed by our usual factorization. So I mean, here again, we have the situation, this guy, his product, doesn't show up anymore at other places. So this just factorizes into this, phi of this times phi of the rest. So this, and the same for this guy. So we can also take this out. So what we get is phi of A3, A3, we're taking this out, and then we're also taking this out, times phi of A4, A4, but then we are left with a situation where we cannot take out neighboring pairs anymore. In this case, we are left with phi of A1, A2, A1, A2. And I mean, if our partition is crossing, then we must arrive at some point at such a situation. Because otherwise, we could strip away everything up to the end, and then it would be non-crossing. Okay, so we arrive at such a situation where we have alternatingly different variables. Okay, but phi of each of these variables is equal to 0, and the definition of freeness tells me then that phi of this guy is equal to 0. This is equal to 0. Of course, those guys are 1, but this is 0. So the thing which really is responsible for the crossing, that gives me 0 at some point. So maybe this is the crossing situation. But this is 0. Yeah, and so we see that in the free central limit theorem, again, we arrive at a situation where formula where we are summing over our pairings. Each pairing is weighted with this factor g, but in this situation this factor is 0 or 1. So this means the zeros we can throw away, and the ones are the ones which remain and which we actually count. So what we are counting here are the non-crossing pairings. Now the conclusion of all this, the free case is that the limit n going to infinity of the k, well, let's say k is now 2m, because it's even. So this is given by the number of non-crossing pairings of 2m. Of course, I know non-crossing pairings again by this something else. So we write this down. NC2 of 2m. Those are the pairings of 2m elements where pi is non-crossing. So those are what we call the non-crossing pairings. Good. Okay, so again, at least we have that the moments in this limit are again given by natural numbers, which count something. And now, of course, it just remains to see that those are the numbers of this semicircular distribution. And I gave you some explicit numbers for the semicircle, and so one should see that these are the same numbers. Okay, and this, maybe I will do in the next lemma, together with this, it proves the free center limit theorem. So we will postpone this next lemma because it's important in for itself. Those numbers are really the numbers of the semicircle, are the moments the semicircle will be treated in the next lemma for those. Okay, but then together with this gives us a proof of the free center limit. Free center limit theorem, which was 2a. Okay, this ends our proof of both the classical and the free center limit theorem. Good. Now you know the statement that the numbers of non-crossing pairings is the same as the moments of the semicircle. Right? The semicircle, I gave you an explicit formula. You should actually calculate this in the assignment. And those formulas were important numbers, which are called Catalan numbers, and so we should talk a little bit more about this in the next step. To really see what are those numbers. Yeah, in any case, with this combinatorial approach, one sees this analog nature of the classical and the free central limit theorem maybe much more clearer than by just presenting these analytic formulas. In the classical case, you go to the normal distribution. In the free case, you go to the semicircle. But as analytic objects, it's not clear why they should have anything to do with each other. But here we are just saying that actually the moments of the normal distribution are just given by counting all pairings, and the moments of the semicircle are given by counting non-crossing pairings. And this makes it clear that those two distributions should be of very analog nature. Okay, so let's go a little bit more on trying to understand these numbers here. Okay, so let me denote them by Cn. Our definition of Cn at the moment is this is given by a number of non-crossing pairings of 2n elements. And the question is, what are those numbers? So can we say anything interesting about them? And the first is, maybe the most interesting thing about them, which we can say is a recursion. Those numbers satisfy some recursion. So namely, Cn satisfy following recursion, that namely Cm can be recursively calculated in terms of smaller ones, namely summing from 1, take from 1 up to m, and then I take Ck minus 1 times Cm minus k. This is true for all m greater than 1. So this is a quadratic recursion. And you see on this side I get only smaller terms. So you see I get here terms where the indices are summing up to m minus 1. But I also get the term C0. So maybe it's not clear what C0 is. C0 is a number of non-crossing pairings of an empty set. It's not clear, but it makes sense to say this is 1. Usually our partitions should not consist of empty sets, but we will tell you the decomposition of the empty set, maybe that's wow. So it makes sense. So we put C0 equal to, and that's how this recursion has to be understood, because there we need C0. Good, okay, and of course, if I have C0 equal to 1 and this recursion, then this defines me uniquely a sequence of numbers, and so there's a unique solution actually to this, and this solution is actually given by the moments of the semicircle as I had it in the free centimeter theorem. So maybe the second part here is that one can solve explicitly this recursion. Solution to this recursion is given by Cm is numbers which we had in the free central limit theorem, namely 1 over m plus 1, and then 2m choose by normal approach. Good. Okay, and the numbers appearing up here are really very important numbers, showing up in many contexts, in combinatorial contexts, counting many combinatorial objects, and they are called Catalan numbers. Okay, so I mean, either you can say Catalan numbers are those explicitly given numbers, but very often it's very advantage to have this recursion, because that's very often part of that you have a combinatorial problem which has a kind of recursive structure corresponding to this. So let me make this definition that those numbers we are calling Catalan numbers. So these numbers Cm. 0 from this lemma, and I are called Catalan numbers. Yeah, after Catalan. Good, and maybe, okay, we still should prove this, but maybe before we do this, let me just write down explicitly a few of them and see what they concretely are. And maybe use this recursion to get them. First, few Catalan. Okay, first one, C0, this is 1 by definition. Okay, and the other ones, we should be able to calculate out of this recursion. So, what is C1? So if m is equal to 1, then we have just one term, and this is C0 times C0. C0 times C0, this is 1 times 1, which is 1. So the first is also 1. And what is C2? There we have two summons. So this is C0 times C1 plus C1 plus C0 plus C0 times C1. Oh, okay. So this is 1, this is 1, and this is 2. C3. This is C2 times C0 plus C1 times C1 plus C0 C2. So we have to multiply the guys where the two indices add together to 2 minus, to 3 minus 1. So 2, 2, 2. And what is this? This is 2 plus 2 plus 1, which is 5. And in the same way you can go on. So the next ones are C5. Next one is C4. This is 14. C5 is 42. C6 is 132, and so on. And you can, of course, you should also check if this really is given by this complete formula. Okay, so let me prove this, and in particular, let me prove this recursion. I mean, at the moment, the CMs are defined as the number of non-crossing pairings of this guy, and we would like to see that they satisfy this. And then maybe this here, this actually maybe is the assignment, to see that the solution of this is given by those numbers. Yeah, so the first is the more interesting, because there you really see, and this gives you the recursive structure of the problem. Counting non-crossing pairings, again, is a recursive problem, and this recursion relation for the Catalan numbers corresponds exactly to this recursive nature of this problem. Good, so what do we want to do? We want to count non-crossing pairings of numbers 1 up to 2n. And we do this in a recursive way. Use the proof. So we want to understand what are non-crossing pairings of 2m elements, and we do this in a recursive way by looking on, let's say, more or less how we did it when we counted all pairings. We just look for the first block, how many possibilities for the first block, and then essentially we are left with the problem of n minus 2 or k minus 2 number of points. So this was also a recursive way of counting. But then it was very simple, because if I take the first block, I have so many possibilities, and then I'm left with the same problem of k minus 2 points. It doesn't matter how the points are distributed. And here we are doing essentially the same. We look for the possibility of the first block, and let's say the first block is the block which contains the number 1. So the 1 must be paired with something, and then we are left with a problem of k minus 2 points. But now this problem is not just connecting the remaining points in a non-crossing way, because we also have to take into account that we should have a crossing as the first one. So, okay, pi in nc2 of m must be of the form. I have the first block, which means 1 must be paired with something, so L is a number from 2 up to 2m, and then I have a rest, and the rest is just is a non-crossing pairing of the remaining points. First of all. So I write here union p twiddle. Where is p twiddle here? This must be non-crossing pairing. It consists of the other blocks of pi. So this is a non-crossing pairing of the remaining points. So this is 2 up to minus 1 and plus 1 up to 2n. I just have removed the point 1 and n. So this is a non-crossing pairing there. And this here is of course just the block containing 1. Okay, but I mean, of course, it's not enough to ask you for any non-crossing partition of the remaining points. I mean, this would avoid crossings among the blocks which are here, but I also should make sure that I don't have a crossing with the block here. So my situation is that I have my points 1 up to 2m, somewhere here, it's 2m. Then the 1 is paired with this L. And then I have the remaining points. And now, of course, this pi twiddle cannot pair anything from here with anything from here, because otherwise I would get a crossing with this block. No? Okay. So this means the pi twiddle must actually decompose into a partition of those points and a partition of those points. And these are necessarily, of course, non-crossing partitions here and non-crossing partitions here. No? So those two guys here, those cannot be connected by twiddle, because otherwise I would have a crossing with the block 1n. So this means this pi twiddle actually decomposes into two, a non-crossing partition here and a non-crossing partition here. So twiddle is actually the union of a non-crossing partition for those points and another non-crossing partitions for the other points. So this one is a non-crossing partition, partition pairing, all the guys are pairings, of the points lying between 1 and L. Those are points 2 up to L minus 1. And pi 2 is a non-crossing partition of the points which are coming after the L, so from L plus 1 up to L. Non-crossing pairing of L plus 1 to L. Good. But of course now I have satisfied all constraints. This means whenever I take now such a block, and I take a non-crossing partition here and a non-crossing pairing here, then this gives me a non-crossing pairing of the whole thing. So this means my counting is now recursively reduced to count how many possibilities do I have for choosing this first block, and then I have the number of non-crossing pairings here multiplied with the number of non-crossing pairings here, because I'm for any guy here I can take any up to any guy here. So this means my CM, counting the number of non-crossing pairings of 2m elements, is now given by, okay, choosing the first block. And so for the first block, I can choose this L. So I'm summing over L from 2 up to 2m. Then I have the number of non-crossing pairings here, number of non-crossing pairings for the elements between 1 and L, which is 2 up to L minus 1, times the number of non-crossing pairings for the elements coming after L. So these are the non-crossing pairings of L plus 1 up to 2m. Good. And of course, this is now just again the same problem as before, but for a smaller number of points. And in particular, it is also clear that the number of points which I have here must be even. Because if I have odd number of points, I don't have non-crossing partitions. So this means this L here, okay, if L is odd, then it doesn't contribute, because then those guys here are odd and odd. So this means what I have here is actually the L is only running through the even numbers, because for the odd numbers, those terms here are 0. So this means what I have here is the sum, that the L is only running to the odd numbers, to the even numbers, and then we say I call them 2. So I'm running over k from 1 to n. So L is now the form 2k. And then k is running from 1 up to n. And then I have here the non-crossing pairings of how many elements do I have here. So the L is now 2k, so I have here 2k minus 1. So I have here 2k minus 2 elements, and the non-crossing pairings of this is given by C of k minus 1. And here I'm going from 2k plus 1 up to 2m. So here I have I have 2 m minus k elements. And the number of non-crossing pairings of this is given by C m minus k. So here I have 2 times m minus k elements, and here I have 2 times k minus 1 elements. Okay, now you see this is exactly the recursion which I have written down here. So this shows that the number of non-crossing pairings satisfies this recursion. And maybe you can take this as a definition of the Catalan numbers. Okay. But of course it's good to see that it's also this, and maybe in an assignment you are asked to calculate it. So now the solution of this is given by this. Maybe the best is this form and power series method. This will be specified in the assignment. Okay, so part 2 of the proof, I'm not going to do here, but so this can, for example, you see by form and power series. Calculations, and this will be done in the next assignment. Good. So this proves that the number of non-crossing pairings is given by those numbers, and those numbers on the other hand are also the moments of the semicircle. So this shows that in the free center limit theorem, our normalized sum converges to the semicircle distribution. Okay, that's it.